Okay, math review part 2. Let's review the dot product. And if you're already comfortable with the dot product, then just skip these. You don't have to watch these videos. Just skip ahead, do the quizzes, and then if you find the quizzes are harder than you thought, then maybe come back here and then check the reviews. Okay. Okay, so what is a dot product? These are the two formulas that we learned, which we have the component-wise multiply and add form, and then we had the magnitudes and cosine form. And even though they're two different equations, they give the exact same result. And we often use that to do the dot product the easy way here, and then from that you could back out what was the cosine of the angle. And then you could get the angle from that if you wanted. Okay, on this form in particular, I want to point out that we could have a two-dimensional dot product, or as I've shown here, a three-dimensional dot product. And in some cases, we may even have a four-dimensional dot product. If we did that, then we would have X, Y, Z, and then we're out of letters. So we go to the next letter. What comes after Z? Well, W, obviously. Well, why does that happen? Well, we ran out of letters, right? So we're gonna have to start going backwards. And the way I like to think of it is actually we're doing a rotation, right? So we go X, Y, Z, W. Just goes around in a circle. Okay. So how do we use the dot product? What is it for? The main way I like to think of the dot product is as the dot product is a measure of parallelness. Now, what does that mean? I mean, okay, first of all, parallelness, that's not even a word. I just made that up. What I'm saying is how parallel are the two vectors? Are they totally parallel? Are they kind of parallel? Are they pointing in opposite directions or what? Let's look at some examples. Here I have two perpendicular vectors. So that's 90 degrees. They're perpendicular. They are totally not parallel. So if I use this formula for the dot product, and notice I'm using unit vectors here, and because they're unit vectors, this is 1, so I'm left with just cosine alpha. If the angle is 90 degrees, cosine alpha is 0, so the dot product is 0. So their parallelness is 0 here, 0 parallelness. They're the opposite of parallel. They are perpendicular. Okay, let's take an acute angle here. So this is less than 90. If it's less than 90, then the cosine of the angle will be some positive number. So the dot product is some positive number. Any positive number means that the two vectors sort of point in the same direction, kinda. The larger this number, the more parallel they are. As the number drops towards 0, that means they have approached perpendicular. All right, let's take an obtuse angle. And I'm showing the angle, same counterclockwise angle here, so it's super obtuse. Any obtuse angle like this is going to have a negative cosine, and that means a negative dot product. A negative dot product means that the two vectors point in opposite directions. They're pointing away from each other. And if they're perfectly pointing away from each other, so that's 180 degrees here, because I'm doing unit vectors, the dot product is exactly -1. If they're perfectly parallel, they point in the same direction, the dot product is 1, anti-parallel, -1, perpendicular, 0. That's a measure of parallelness. Let's give that an example. Say I have a triangle, and I'm hitting it with a light, and I want to know, does the light hit the front of the triangle or the back of the triangle? The way we do that, we'll say we give it a face normal. The normal is a vector pointing upward from the triangle. And here is that normal. And then the light is shining along this direction. So the question becomes, does this light aimed this way hit the paper in the front, or does it hit the paper in the back? So pause it here. And we'll solve that on the next slide. Okay, let's solve this thing. This is a good example, good practice drawing a three-dimensional system. So I have my x and y axis like before, and using the right-hand rule, I'm drawing the z-axis coming out like so. Let's drop these two vectors onto our xyz axis. This first one doesn't have any z components, so that's pretty easy. We'll put the x out at 0.707, and we'll come down negative 0.707 down the y-axis. So that gives us a point right there. Here's our vector. The next one, we'll start by going out negative 0.866. So going this way, 0.866, and we're going to come out positive 0.5 on the z. So it brings us there, and there's no y on this one. So there you go. Okay, so there's our little diagram. It's still kind of hard to tell whether those point in the same direction or not, but that definitely looks like an obtuse angle to me, right? Let's prove it. Okay, let's do the dot product. Here's the dot product of those two vectors, and we're just going to use the form. You just take this times this plus this times this plus this times this. Let's write that out. So the x's plus the y's plus the z's. And note, I am not even interested in this value. I only want the sign of the total thing. And because these are zeros, I don't care. So this is going to be super easy. This is going to give me a negative answer. D is negative. If D is negative, that means the two vectors point away from each other. Cool. All right. The other thing that a dot product is useful for, and you'll hear this term pretty often, is projection. We will say that the dot product is a projection of one vector onto the other. And you will see that this first vector, I'm given it an arrow, so that means it has some magnitude. And the second one is a unit vector. So I am projecting this vector A onto a unit vector B. If we do that with this form of the equation again, since B is a unit vector, that term drops out, and we just have magnitude of A times the cosine of the angle between them. Now, that is going to give us a projection. What is a projection? What does that even mean? Let's take a look at this thing. Let's take an arbitrary vector A and some direction unit vector B, and there's an angle between them of alpha. What is the projection of A into the direction of B? What I mean there is how much of A points in the B direction, right? What I mean is make a right triangle out of this thing. Make a right triangle where the direction B forms the adjacent edge. And then we'll drop a perpendicular, and we'll call that the opposite, right? The projection in that case is then, what is the length of this side? Okay, and that is going to be given by this dot product right there. Okay, we can think of that as how much of A points in this direction B. Cool. Now that's actually something we've been doing for a very long time, well before we learned about a dot product. We've been doing this and we just didn't really realize it. Take a look. Let's take this vector A and just drop it onto an XY axis. And what are we doing? We say this vector A is the X component and the Y component, right? What is the X component of this vector A? Well, that's the projection of A onto the x-axis. We do the same exact thing we just did on the previous slide. We say make a unit vector in the x direction and dot product A and this unit vector x. What do we get? We get A dot x, or magnitude of A times the cosine of alpha. Right? That's what we had done before on the previous set of slides where we talked about sine, cosine, tangent. We learned that the adjacent side was r cosine alpha, right? Where r, in this case, is the magnitude of the vector, and then the cosine alpha. That's the dot product. Okay. We had another name for that. That's just a sub x. A sub x was r cosine alpha. Or instead of writing r, we could write magnitude of a. So magnitude of a cosine alpha is a sub x. Well, that's the dot product. So check this out. In programming, we call that a dot x. And a dot x equals a dot x. Interesting.